Hi, this is Math 1650, and in this video we will be looking at the start of Chapter 7, and in Section 7.1 we will look at estimating a population proportion and finding its confidence interval. In the next couple of chapters we'll really be getting into the meat of statistics, confidence intervals, and hypothesis test. We'll be looking in both of these at proportions and standard deviations. Alright, so for proportions, we are building right off of what we just did in 6.6. We're looking at a normal distribution as an approximation to the binomial distribution. And so we have certain requirements. First, a sample is a simple random sample. Second, conditions for the binomial distribution are met. This includes fixed trials, two choices. Dealing with proportions, we should have a portion of success and a portion of failure, independence, and a constant probability. And then we also are dealing with the normal distribution as approximation, so we'll have n times p must be greater than or equal to 5, and n times q must also be greater than or equal to 5. Alright, so a few things with notation. In this chapter, you'll see P, it's just P, this is the population proportion. It's what we're trying to kind of estimate. Then you'll see P hat, that is the sample proportion. And so these are from the sample, P hat and Q hat. P hat is x over n, so your number of successes over your sample size. You're going to need to know x a lot of times, and if you're given p hat, then it's going to be n times p hat to find x. Q hat is 1 minus p hat, just like q is 1 minus p. Your best point estimate is going to be that p hat, and we're going to build the confidence interval by adding and subtracting the margin of error. Now, the confidence interval, which I'll abbreviate CI, is the range of values used to estimate the true value of the population parameter. In this case, it's going to be the proportion. We'll also look at when it's the mean. But it could be other things, could be standard deviation, which we won't get into that. We have a confidence level. This is the percentage of all possible values that can be expected to include the true population parameter. Percentage of all possible values that can be expected to include the true population parameter. It's another way of saying how confident that the confidence interval contains population parameter. Think of it this way: if you say your interval is from 0 to 100%, the proportion somewhere between 0 and 100%, you can say you're 100% confident that's between 0 and 100, including 0 and 100, because it has to be. If you were to say the population proportion is 35%, well, you're going to be 0 confident because you're only using one value, and chances are it's not exactly that value. One way you can think of it is the regions here that border the confidence interval are where your value, may be too small to really be expected to be the true value, and where your value is too high. Everything else in between is small enough or large enough or small enough to be right there and around what you expect it to be. Right? And we call those borders of the confidence intervals the critical values. These are the z-scores that border the confidence interval. Used to determine the margin of error. Now we're going to really write the critical value as a positive z-score, especially when we do the formula itself, but it's technically positive or negative in the side, and with the normal distribution it will be symmetrical. So we see the 95% in the photo, in the graph up here, is directly in the center. So the borders are at, for that, negative 1.96 and a positive 1.96. And the way it's found is it takes alpha, which is 1 minus the confidence interval. So I'll write down here, alpha is 1 minus the confidence level, and divides it by 2. So 95%, you're dividing that 5% by 2, and you look at finding the z-score when the area equals 0.975 and 0.025. For 90%, you divide the 10% by 2, and you have 5% on both sides. I can graph it a little bit for the 90%. For 90%, that means here is 5%. This is 5%, so we're looking at 0.05 and 0.95. For 99%, you're looking at 0.5% on each side, so 0.05, 0.05. So here this is 0.05, this is 0.995. 0.005. 1 0 short here. Okay. The critical values is the z-score of those percentages. So it's gotten just like we've gotten the other z-scores. If we'll look at 90% where your alpha is 10%, we're doing 0.5. And you see it's a negative 1.645, and then we're doing 0.95, which is going to be at the positive 1.645. So that way the 90% in the middle, 5% on this side, gives those z-scores negative 1.645. 5% on the top side, you get a z-score of 1.645. And then 95%, that's 5% that we're dividing into. So we do 2.5%. You get the negative 1.96. and we'll do 97, oops, 0.975. You get the positive 1.96. And then we go further, 0.005. That's negative 2.576. And 0.995 is positive 2.576. Okay, so that's how these values as your critical values are obtained. And these are the common values. So when you have a confidence level of 90 or 95 or 99, you can kind of just hopefully remember, or you can look it up on this table. All right, so let's say we want to find the critical value for a confidence level at 88%. Well, alpha is 12% or 0.12. That means alpha over 2 is 0.06%. And so your critical values, I'll do this on the graph, this is 88%, this is at 6%, this is at 6%, so we're at 0.06 and 0.94. And we'll see that it's going to be positive and negative, the same value there. 0.006 is negative 2.51, and actually I may went too far with that. Yeah, too many zeros. Hold on, second. Negative 1.55, and then 0.94. Yeah, 1.55. So it's a positive and negative z-score of 1.55. So negative 1.55, positive 1.55. Okay. Margin of error represents the range where the true population parameter is expected to be given a certain level of confidence. There is a formula to find it, z alpha over 2, which is the z-score, why we gotta find the z-score, times the square root of p hat q hat over n. And then we take that confidence interval and we add it and subtract it to the sample proportion, find the interval itself. Alright, so the steps to this. We verify assumptions are satisfied. We calculate the critical values. Z alpha over 2. Evaluate the margin of error. And find values p hat plus e, p hat minus e, and then we construct the confidence interval. There's three ways we can write this confidence interval. P hat minus e less than p hat plus e, and we would actually have the values there. We wouldn't write necessarily the proportion minus the margin of error. We'd just do the math and have one value there. We could write it as p hat plus or minus e, which there we would have two values. And then we can write it as just p hat minus e, comma, p hat plus e. Okay, on StatDisk you will see it like the top one. So let's get into a example here. A marketing company wants to estimate the proportion of satisfied customers. A random sample of 500 customers is surveyed, and 360 report being satisfied with the company's service. Construct a 95% interval for the true proportion of satisfied customers. So 360 out of 500 customers were satisfied. That is 72%. What's the percentage on 0.72 or 72%? That's your p hat. Your q hat is 1 minus that, so your q hat would be 0.28. Right. So now we need our z alpha over 2. We're at 95% confidence interval. So we go back up to that table. That gives our z alpha over 2 as 1.96. Now we want to evaluate the margin of error. So we have 1.96 square root of our p hat times our q hat over our n, which n is 500. And write that down while we're going to. X was 360. And that value comes out to be 0.039. Right, so our p hat minus e is 0.72 minus 0.039, and our p hat plus e is 0.72 plus 0.039. So we get 0.681 and 0.759. So we can say that our confidence interval then is from 0.681 to p to 0.759. Or we can write it as 0.72 plus or minus 0.039 or 0.681 comma 0.759. Either way, it's still given the interval. Alright, so now we're going to look at doing these on StatDisk. Now, StatDisk, there's certain things you do have to write down, but most of it is once you do a couple little things, pulling out certain information, you're just going to be plugging values in and getting the results. So first, what you need. All right, so in the next sample or next example, in a medical study, a random sample of 200 patients was tested for a specific disease, and 30 of them were found to be infected. Estimate the true proportion of patients who have the disease within a 90% confidence interval. So confidence level is your 90%. Your N is 200. 200 patients were tested. Your X is 30. Right. So now we'll go into StatDisk for the confidence interval. Now look at here, you have select analysis, select confidence interval, select proportion 1 sample. Right. So we'll select analysis, confidence interval, and then proportion 1 sample. And it's going to ask for 3 things: confidence level, We said that was 90%. Sample size 200. Number of successes is 30. That's all it needs to do this. We see a margin of error that's 0.042. And we see a confidence interval. Now we won't worry about the Wilson score, but the confidence interval is here, 0.108 less than P or less than 0.192 or 0.108 comma 0.192. So that's your intervals. Or you can say the last way of writing it, you're using the margin of error. We have to find p hat. We didn't find that. 30 over 200 is 0.15. So we can say 0.15 plus or minus 0.042. Alright, so status is very easy to get if you just know what information to put in. So we'll do another one. Quality control manager is interested in proportions of defective items produced in a factory out of a sample of 1,000 items. So n equals 1,000. 45 are found to be defective. So x equals 45. Calculate the 99% confidence interval. Confidence level is 0.99 for the proportion of defective items. So before we do this in StatDisk, and we find the p hat, 45 out of 1,000. Which is 0.045. Alright, so let's put this into StatDisk. So 0.99 is your confidence level. 1,000 is your sample size. And successes is 45. Alright, so margin of error 0.017. Right, confidence level is 0.028, less than P, less than 0.062. Right, so we can write this as 0.028, comma 0.062, or 0.045 plus or minus 0.017. Alright, so do one more example here, and we're going to look at another thing that deals with proportions before we end this video. Hospital wants to estimate the proportions of employees who have received a flu vaccine. Out of a sample of 150 employees, 102 reported being vaccinated. So X is 102, N is 150. So P hat is going to be 102 divided by 150, which is 0.68. So 68% of the people relatively or around that got the flu vaccine. We're going to look at finding a 95% confidence interval for the proportions of vaccinated employees. So confidence level is 95% or 0.95. Okay, so go to StatDisk, put in 0.95, 150, 102. So margin of error is 0.075. Confidence interval is 0.605, less than P, less than 0.755. Alright, so we can write this as 0.605, comma 0.755, or 0.68 plus or minus 0.075. So somewhere between about 60.5% and 75.5% is the true proportion of vaccinated employees. Alright, so with this next thing, we're going to be looking at determining sample size. Now, there's a couple ways we're going to do it, a couple formulas we're going to use. It all depends on whether we are basing this on previous research or not basing it on previous research. If we are basing it on previous research, then our sample size is determined by z alpha over 2 squared times p hat times q hat over e squared. That's your margin of error squared. This comes from the margin of error formula. Where it just solved for n. Okay, so they squared both sides, that's why e is squared. Then they multiplied n over and divided the e squared over. So that's why your z alpha over 2 is squared, your e squared, but your p hat and q hat are not squared. If you don't have any previous information, then what they do is assume the worst case scenario, and the worst case is that it's equal 0.5 and 0.5. For p and q hat, resulting in 0.25 there. And so you can either keep it as 0.5 times 0.5 or both, or you just use 0.25. It's going to result in the highest sample size. Okay, so a recent campaign was designated to convince car owners that they should fill their tires with nitrogen instead of air. That costs about $5 per tire. Nitrogen supposedly has the advantage of leaking at a much slower rate than air, so that the ideal tire pressure can be maintained more consistently. Before spending huge sums to advertise the nitrogen, it would be wise to conduct a survey to determine the percentage of car owners who would pay for the nitrogen. How many randomly selected car owners should be surveyed? Assume that we want to be 98% confident that the sample percentage is within 3 percentage points of the true percentage of all car owners who will be willing to pay for the nitrogen. Alright, so we are going to assume no new information here. So we'll use n equals z alpha over 2 squared times 0.25 over e squared. Now, we have to find the z alpha over 2, that's first. And so with the 95% confidence interval, we're looking at alpha equaling 2%. So alpha over 2 is equal to 1%. So we'll plug in a 1% for our normal distribution. And we get a z-score, or z alpha over 2, of 2.33. We're not going to do the minus sign, it's just the absolute value there. Because it's technically plus and negative. And so for the sample size, it's 2.33 squared times 0.25 over 3 percentage points. That's 0.03. So 0.03 squared. And we get 1508.03. Now we are going to round this to the nearest whole person, but we have to always round it up. So even though it's 0.03, so the nearest is 1508, we're going to round up to 1509. Okay. Now, if you're doing this on StatDisk, you may have a little bit of a discrepancy because I'm rounding the Z alpha over 2 as well. So it could be off a little bit. So we'll check it on StatDisk here. Alright, so what if we have previous research suggesting that 65% of car owners will pay for nitrogen? Well, it will reduce our sample size. And so we'll have N equals 2.33 squared. That's not changing. P hat is now of 65%, so times 0.065 times 0.65. Q hat is 0.35 over 0.03 squared, which is a margin of error. I get 1373. And of course I rounded it up, so I have 1372.3. So I'm rounding it up to 1373. Okay. On StatDisk, if we wanted to do this, we would do analysis, sample size determination, estimate proportion. It's going to ask for a couple things. It'll ask for the confidence level. We said 98%. Margin of error is 0.03. So we evaluate this. This is going to be the top answer. So we're looking for about 1509. We get 1504. So it's a little lower. That's because we rounded our Z alpha over 2. And if we add in the 0.65 as the estimate of our proportion, we're going to be 1369. So again, pretty close to the 1373 we got. I would suggest to do this more on StatDisk because your answers are going to be much closer, and chances are you won't have Pearson tell you your answer is wrong just because it's too far off, but it's really just due to rounding. Alright, so a couple of examples here. A company wants to conduct a survey to estimate the proportion of customers who are satisfied with their service. The company desires a margin of error of no more than 4%. So margin of error is 4% or 0.04. Confidence level is going to be 95%, so 0.95. Rewrite the 9. What is the minimum sample size? Alright, so again, we're going to do this on StatDisk. So 95%, 4% error, take out this proportion, and we get 601. Right, let's say previous surveys indicate that about 60% of customers are satisfied. Where's the minimum sample size with the new information? So the new estimate of P is equal to 0.6. So we add that in, and it reduces it to 577. Alright. In a study for vaccines, a medical researcher is planning a study to estimate the proportion of people in their population who have developed immunity after receiving a new vaccine. The researcher wants the margin of error to be no more than 5%. So E equals 0.05 at 99% confidence level. Since this is a new vaccine, the researcher assumes the proportion of people developing the immunity is around 50%. So your estimate of P you can put at 50 or you can leave it blank. I'll do both to show what sample size should we use to achieve this level. Right, so 99%, 5% margin there, and then estimate of P, I'll leave it blank for now. We get 664. And then if you would do at 50%, again, you get 664. There's something message below. Assume a proportion of 0.05. I see. And then if you actually put in the proportion of 0.5, doesn't have that, but it's still the same sample size. All right, so this is the end of 7.1. In 7.2, much of it will be the same. We'll just be looking at the mean, so a couple little things will be different with it, and you'll be going to a little bit different of boxes on StatDisk, but it's pretty much the same area. I'll see you then. Bye.